Okay, I'm going to take you through the methods of how I synthesize transition metal dichalcogenides. If you recall, the short version of that word is TMDC. So my mentor was Dr. Brian Leroy in the physics department here at the University of Arizona. So to recap my question, which TMDC crystals can be synthesized with two specific methods, and then which of these methods and which compound are best used for a back-gated field effect transistor. And in particular, I'm focusing on three compounds: tungsten selenide, tungsten sulfide, and tantalum sulfide. Here's an agenda just to give you an outline of the path I'm going to take for the rest of the power presentation. All right, so my growth methods. The chemical vapor transport reaction method is basically you are putting the elements of the compound together with a transport gas in a vacuum tube. You're heating it on high until everything is a gas, and then it will deposit a crystal of the compound on the other side of the tube. You have to put it on a temperature gradient, so one side's hotter, one side's cooler, so that the crystal does form on the cold side. While I was researching that method, I found that there is a similar method known as sublimation. So the difference in between these methods is that you take the material finely ground, put it into that vacuum tube, and you heat it so high that it becomes a gas, and then it will form a crystal above where the original material started. The biggest difference is that you do not need that transport gas like you needed in the previous method. Thus, you have a pure crystal in the sublimation method. So, some equipment. In particular, I needed what's known as a 3-zone furnace. If you noticed in the methods, I need to be able to put the vacuum tube over 2 different heated zones. So a 3-zone furnace gives me that ability. Additionally, it allows me to do 2 sets of compounds at the same time as long as they can share a certain temperature. I want to introduce you to Bertha and Betty. I got to know them quite well this summer. These are typically 3-zone furnaces, very large furnaces, and they do work very well. So here are some of the specifics. I started 4 batches. I completed 3. The first batch, if you'll notice, the first one is actually shaded. There was a zone failure, so unfortunately this sample did not work out well. In the second phase, I actually conducted the tungsten sulfide at a lower temperature, where the tantalum sulfide is actually on the high for this compound. If you notice that the timeline is different because we actually used tongs to pull the sulfide out ahead of time and then just allowed it to cool at room temperature. On the third batch, we ran the tungsten sulfide and then tungsten diselenide at much higher temperatures for longer periods of time. And then batch 4 is the tantalum sulfide at a lower temperature, and these are running for an extended amount of time as well. So once I had the crystals, I needed to exfoliate them. And the method that we are trying to use is Scotch tape method because it gives us a cleaner monolayer. All 3 of the compounds exhibit the property that you need to use less is more when exfoliating. So a gentle force when you're pulling it apart, and then less pulling apart of the tape in general. And that yields more monolayers and larger monolayers. In general, tungsten sulfide was great. It gave us the correct size. It readily gave us the monolayers, and we didn't need to do anything else to help transfer it to the substrate. Tungsten selenide gave us thin layers almost immediately. However, it takes a lot more coaxing in order to get the monolayer. So this one will need a little bit more technique in order to extract that monolayer. The tantalum sulfide, like the tungsten selenide, needs a little bit more technique for the monolayer. However, the tantalum sulfide does not transfer to the substrate very well. Most of it just stays on the tape and sticks to the tape and won't actually transfer to the substrate. And even with a heated transfer, it did not improve the amount of material that went to the substrate. And this is the actual Scotch tape that we used. It's got a special acid on there to reduce the amount of residue that transfers to the substrate. So here are my results. Okay, so this is from the first batch of tungsten selenide. If you just notice, it's a fine crystal powder. The fact that it shines is a good indicator that we are on the right track. So that means that there are flat surfaces. And this is our third batch, or the batch 3 of the tungsten selenide. This was run at a higher temperature for a longer period of time. This actually gave us larger crystals. In particular, this arrow is pointing at a very large crystal that came out of the sample. We still have a lot more of the powder effects. And at the other side, we actually got some pretty decent flakes from the sample. So in order to confirm that we had the right structure, because in particular we need specific structures that will that allow us to exfoliate it down to the monolayer, we run it through something called X-ray diffraction. What you need to take away from this picture is that the gray down here indicates what we expect to get if it's the right structure of hexagonal. The red is what we actually get from the sample. If it matches up, we're on the right track. This, for the first batch of tungsten selenide, it did match up, and we do have a hexagonal structure. Tungsten sulfide, the very first batch I don't have up here because that one failed due to a lower temperature. The second batch, this was at a lower temperature for not very long. We have a kind of more of a finer powder, small little bits of flakes. They were exfoliable. And the batch 3 was at a higher temperature for a longer period of time. We got kind of larger flakes and nice big clumps that were kind of easier to exfoliate. Tantalum sulfide, in the first batch we got a pretty nice consistent crystal powder. It's very pretty to look at, and it does shine, which gives us the flat planes. This of course is at a higher temperature, which indicates it should be an octahedral form. Which does not exfoliate in the other 2 compounds, but does exfoliate in this compound. Batch 4 is still cooking, as indicated by the fact that they're in the furnace. So thin layer analysis. Once we have these things exfoliated, we want to look at them. And the way that we need to confirm that, we go through different processes in order to confirm that they're actual monolayers or thin layers. So the first method is particular to the tungsten sulfide and the tungsten selenide. It's called photoluminescence. Basically what you do is you shine a laser at the substance. It excites the little electrons in the substance. Once the electrons relax and release, it releases a photon, and that's what we measure. The release of this photon actually measures the amount of energy it takes to get from up here to down here, which is what we want to see in the semiconductors, because it indicates the band gap. For the tantalum sulfide, we relied on Raman spectroscopy. Basically what that means is we shine a laser, and then what's reflected back is what we measure. In particular, at certain wavelengths, particular to a certain compound, you get a lot more feedback. So there's a particular wavelength and a particular peak of Raman spectroscopy that we're looking for to identify that we do in fact have the right material. The next form of analysis is we run the samples through the atomic force microscope. Basically, it's a microscope that can measure at atomic levels. So this thing can measure how high it is from the substrate up to the top of the sample. So here's a picture of the tungsten selenide sample from the first batch. And we were on the right track, so we've got the repeated hexagons. And then here is the actual thin layer that we analyzed. But as you can see, it's still pretty dark and kind of opaque, so not as thin. This is a photoluminescence feedback. The fact that it has double peaks indicates it still has an indirect band gap. So this isn't quite monolayer, but it's approximately about 3 to 4 layers. This is the AFM of that image. The darker areas were referred to the thinner part of that image. The lighter areas refer to the thick. The arrow is pointing to the thinner portion of this sample. This is the step height. So from here, from the bottom, around here represents the substrate. This is the distance from the substrate to the top of the sample. It's about 4 nanometers thick, which corresponds to 4 layers. Tungsten sulfide, this is the sample that we measured. There's a very light blue area here that's practically thin, or that's very practically see-through. That is our expected monolayer. This is the photoluminescence. We measured the thicker part, and then we measured the thin part. The fact that there is one layer on the, or the one peak on the thin part indicates that it is in fact one layer, because now that indicates it's the shifted direct band gap. The fact that there are 2 lumps on the bulk indicates that that is the indirect band gap. So this is what we want to see with the photoluminescence, the 2 to 1. Tungsten sulfide, again, here's the sample under AFM. You can see the darker area, it's very dark, is the thinner piece. The arrow is pointing to that piece. Here's the step height from the substrate up to that portion. It's approximately 1 nanometer thick, which means it's 1 layer. Tantalum sulfide, we haven't measured this one yet, but this is what we're looking to measure. And we're expecting this to be about 2 layers. My acknowledgements, here's goes to Dr. Maria Teresa Velez. She's the one who made this program possible. My mentor, Dr. Brian Leroy. The lab, to Matt, Shang, and Christian. The glass shop, and you can read the rest. A lot of help from the U of A campus. Here's my references and any questions. Now that had my results in it too, so it's, yeah, I kind of expected to go over. Because the methods is just 8 minutes long, right? And then we still have another 7 minutes for results.
You have 20 minutes total for the
yeah.
final presentation.
So 5 for the introduction, 8 for methods, and then that should be 7. Yeah.
Is it 15 or 20? Because somebody said 15 and now, is it?
We have 20 minutes between.
5 minutes or 15? Okay, so 15 and 5. Got it.
15 for the whole presentation?
Yes.
Okay.
But the whole presentation is 20 minutes. Or the entire time you're up on stage.
So you're going to speak for 15, right? And then 5 for questions.
Okay, so we only have 15 minutes to do everything. We need to make sure we have 5 left over for questions.
Yeah. And the way my professor said it was just giving 2 minutes a slide, so you end up with 7 or 8.
Yeah. Yeah. Okay.
So feedback.
Define what band gap energy is. Like, I don't remember if you defined it earlier.
I did, and I briefly went over it. And I think I'm going to have to, because that's actually what's kind of significant about that. So I'll make sure, because I do briefly go over the band gap in the introduction.
One, I thought, especially since you had so much, I thought it was a really good idea to do your outline. Like you kind of give an outline of the project. But I think you kind of just, you said this is an outline and you went to the next slide. I think reading through the outline would be really helpful. It just makes it really structured, or at least giving everyone enough time to read it. It was kind of fast. And then also in the results section, it kind of got to more like a, and this, and this, and this, right? And I think since it is, like it obviously is like really important what you're doing, I think there could be, I'm not exactly sure how, but a way to like structure it where it sounds like more important. Kind of when it's, and this, it loses its importance as the
Yeah, because I'm going too fast.
rolls on, I think, but yeah.
So, yes.
Yeah, I think for me, what would have been helpful for this presentation, because what I got from it is that you do 2 types of method analyses. You do the analyses as a method, and then your measure is a method. So maybe if you should have just taken those 2, slapped it on your method section first, it would have been your methods. That's what I took from it. I don't know, it might not be because you're hard sciences.
No, I'm trying to understand what you're talking about this.
Analysis method is a method.
Yes.
But then your measure is what you should.
Is another method.
So if you could just put those 2 together, that sums up your entire method. And then you could have left out the results. And then you could have left out the results and you could have had your method section right there. I'm not making sense, am I?
Well, because what I'm concerned about, the reason I waited to explain it, because I'm worried that by the time I actually get to it, yeah, people won't understand what it is. So.
I lost in the results, basically. Because you put the results right in the middle of both of those.
Yeah.
Just remind me again, you have 3 different compounds that you're looking at, right?
Yeah.
So does one take precedence over the other? They're all sort of the same. So what I'd say is, are each three absolutely necessary to talk about in equal measure? So.
Well, one, yeah, well, they're all two are semiconductors, one's a superconductor.
So maybe you just
The-
want to make those two distinctions. The semiconductor ones, you could sort of say, here's
Yeah,
the one, it's
okay.
going pretty well, and then say, this is sort of what we did with the other one, but given time constraints, if you'd like to talk about it, I can talk to you after this presentation.
And that would reduce it down. Yeah, that would reduce it down. Less to talk about.
Do you know if they're natural occurring compounds?
Actually, that's the reason why I'm synthesizing them, because they don't. This particular form doesn't occur in nature. So I have to synthesize it in order to have what we need to look at. Yes.
Word thing. Try saying, you know how you were saying, as you can see, try to say observe.
Observe. Yes.
It flows better, and it's
Mhm.
going to help you, believe it or not, that little like 2 seconds it takes. Observe the monolayer. Like,
Observe the monolayer.
yeah, observe.
So where did I lose? Yes.
You lost me when you put the results in the middle, because you're giving me your measures. To me, your measure was your conductors, your machinery.
Okay.
And then you give me results, and then you tell me your analysis method is this. So if you would have told me my measures are these, my methods for analyses are these, then it would lead to your results being this. That just seems like a more linear flow.
Do these pictures add anything to you guys? Or if I just left this out, made it a table and said, hey, we got the structure based on X-ray diffraction?
No, I think they help, but, they could be on, they don't need their own slide, maybe. Maybe if they were just like, it depends on how big the presentation, I mean, the poster is, I mean, or the whole screen is. Because, I mean, if you have room where they can be on the side, you can still get something out of it, then they can go with the other stuff, and it just adds to the thing. But if it's too small, then it's pretty simple.
Yeah, because then I could just result it, because it's kind of like, so here are the results of what I've cooked, and now we're going to analyze it.
Yeah.
That might be nice.
Maybe explain what the crystal thing was, because you said, oh, that was pretty important, and then I wasn't sure exactly what,
That the crystal,
or like the arrow. Or
Oh, on the picture?
Yeah, on the picture.
You're
You
right.
just had a,
oh, I had the arrow, yeah, the arrow was
Yeah.
pointing to the thinner portion of the sample, yes.
This is just kind of, this is maybe more of a question, because on the results section and the methods, I feel it's not so much, it's not like the introduction. I think it's kind of hard to memorize what you're speaking about. So I mean, I know for me, I was basically reading off it, and I think
Mhm.
I saw a lot more this time people were looking at the slide as opposed. Do you know if maybe we're going to have be able to, like in the other room, have the computer in front of us? Because that lets you kind of at least not have your back to the audience the whole time during that section. Because I
I've
mean,
never been
it's
in
hard.
that room, so.
Okay. It's kind of hard to like
It
read
is
your results,
distracting.
you know, off. You kind of have to look at, I mean, I'm not going to memorize mine.
Yeah, I actually have note cards set up, and I
Okay.
totally forgot them.
Oh, well, that's fine.
Yeah.
Okay.
Yeah, because I was just I usually have my note card so I can glance
I
down.
was glued to mine.
Yeah.
We're planning on a mission to go look at the room.
Perfect.
So, like,
Good deal. All right. That was my only.
Okay. Well, we have to move on.